Okay.
If there's space to your left, everybody shift over. It will be a bit easier.
Hi. So, hi. So this talk is a very short introduction to Netmap and how you can use it to implement virtual network functions. So what is Netmap? We have been talking about DPDK, PF ring, XDP, and so on. So Netmap is just yet another independent API to for direct access to NIC, transmit and receive functionalities in user space. So the use case is the very same as DPDK and PF ring and so on. The idea is that you have a NIC and you open that in Netmap mode, and once you do that, you are able to temporarily stealing that from the network stack and use that with a very batch-oriented and efficient API for fast application, networking application. So it's very important to know that this is implemented within the operating system kernel. For instance, differently from DPDK. Should I louder?
Try to speak louder. Really
louder. Okay. Sorry. This is implemented in within operating system kernel, and we will see why this is important later. It's included in FreeBSD and also in Netmap, also in Linux as an auto-tree kernel module. So these are the design principles behind Netmap. I think those are important because of the very same design principles also behind the things like DPDK to some extent and DPDK, PF ring, and XDP. So the first and most important one is batched operation. So the idea is that whenever you want to talk to the NIC, for instance, to tell the NIC to transmit packets and receive packets, you need to do that. You need, for instance, to tell the NIC to transmit many packets at once, because talking to the NIC is expensive. And in general, when you do packet processing, whenever you have fixed costs like locking or lookups, try to for instance, take a lock and process with that many packets. This is important because the fixed cost can be amortized over many operations. The second principle is pre-allocation of packet buffers. So in essence, try to avoid dynamic allocation of packet metadata. Like for instance, in Linux, you have skbuff that you need to allocate, and you need typically to allocate and deallocate skbuff metadata structures for each packet that you process. Third, zero copy access to packet buffer. So the idea is that your application should be able to directly read and write packets in its address space, and the NIC can DMA packets, for instance, directly in the application address space. So you don't need the traditional copy across user kernel boundary. Fourth, kernel provides the protection. It means that your application cannot crash NIC, your application cannot crash the system. So, for instance, in Netmap, the application cannot have direct access to NIC registers and rings. This is very important because all the protection and isolation you need is provided directly by kernel. And last, you must have the possibility to use full synchronization. So, for instance, frameworks like DPDK rely on busy waiting, even if there are other options. But with both Netmap and XDP, you are able to actually use standard synchronization means like poll system calls, select system calls. You can wait for packets to come or wait for egress space. More on this later. So the data structures used by Netmap are very simple. There is a Netmap interface, which is just a bunch of pointers to Netmap rings. Rings are basically an abstract representation of hardware queues. So you can have one or more receive rings or one or more transmit rings for each Netmap interface. And a ring is just a circular array of descriptors with producer and consumer indexes. And all of these data structures are contained in a so-called Netmap allocator. So the idea is that you may have multiple NIC ports on your machines, and a single Netmap allocator may serve more than a port. So the allocator is a domain of trust, meaning that the only applications that are working on the same allocator must trust each other. If you don't want to trust, just use separate allocators. And the basic idea is that in order to access those data structures, so basically rings and buffers, you want to open a special device, and then you can use an mmap operation to make those data structures available in your application. So a Netmap ring, as I was saying, is an abstraction of a real ring, the real hardware ring. So what happens is that applications operate on the abstract ring, and then they use a special sync operation to sync the state of the abstract ring to the state of the hardware ring. So there are 2 pointers. This is the abstract ring. There are 2 pointers here, head and tail. So the meaning of this pointer is that everything between head and tail is owned by the application. So for instance, for receive rings, those are new packets that are ready to be read. For transmit rings, it's free space that you can use for new egress operations, while the rest of the descriptors in the ring, so everything between tail and head, it's owned by Netmap, it's owned by the kernel. This is an example on how you would process a receive ring, right? So say that your application has many descriptors available, many new packets that you can read. It can, for instance, process 7 new packets and then increment the head index, while the tail is just read only. After incrementing this index, it can sync. There is a special I/O control call to sync a receive ring. So what happens, we have 2 effects here. So everything between the previous position of head and the new position of head is just returned to the kernel, is returned to the system for reuse, so that it can be used for receiving more packets. And if any new packets arrive since the last time we synced, tail is incremented accordingly. So in this case, we received 3 new packets. So this is a very simple synchronization between your application and the NIC. Okay. A very important thing that I was mentioning before is blocking versus busy waiting. So the sync operations for both receive and transmit rings are synchronous non-blocking. And basically, they operate on all the rings that are bound to a specific Netmap file descriptor. So the basic idea is that you open a NIC in Netmap mode, binding a certain rings, so you can bind just the receive rings, or just transmit rings, or everything, whatever you like. And once you use sync operations, the sync operations operate on all the rings you bound. And you can use sync operations to implement busy waiting. So if you don't want to block, but this is actually not the usual way you use Netmap, because you may want to actually block, for instance, waiting for more packets to come, or when you want to wait for more space to transmit. And you can use the poll system call, select system call, or on Linux even epoll or kevent. This is supported. So if for instance, you want to wait for more ingress space, you would do the poll-in event. So this is just a standard synchronization. It's very similar to what you would do if you were using sockets, right? So far, I've talked about NICs, so hardware. But actually, Netmap supports many kinds of virtual ports. And virtual ports are important because they can be implemented. They can be used to implement very fast local IPC communication. So, for instance, we have zero-copy pipes. The idea is very similar to Unix pipes. So you have 2 ends, and you can let 2 processes talk, communicate through the pipe. But point is that you can use Netmap pipes using the Netmap API, so you are able to transmit and receive packets in batches, which means that you can be very, very efficient. And also it's zero copy. It's zero copy because you can just swap descriptors, as I will show later. And this means that you can have, independently on packet size, you can have very, very fast communication, over 100 megapackets per second. Of course, this is a benchmark, assuming you are not touching packets, but still, it's an interesting upper bound. We have also software switch, which is designed for virtual machines. So by definition, virtual machines, you want isolations between 2 virtual machines, which means that the switch must copy packets when transmitting from one port to the other port. And because of the Netmap API, the ability to work in batch, you are able to actually transmit 20 million packets per core per port. We also support monitor ports for sniffing, so similarly to what it's sometimes you have a network application using some ports and you want to see what's happening from a separate process. You want to sniff traffic, you can do that with a special port. Today I'm going to talk mostly about the last one, which is pass-through port. So the idea is that you have a network port in the host machine. It can be a NIC, it can be a port of a switch, it can a software switch, it can be a pipe or whatever you like. And I want to export this port within a virtual machine. So the idea of this is basically the idea of network function virtualization, where you want to run your application within a virtual machine. So this is possible with network pass-through. Okay. There are two main use cases. So you have a KVM guest, KVM virtual machine. If you pass through a port of a Valley switch, of the software switch, this is very interesting to implement a very fast local inter-VM networking. So think of two VMs on your machine that are able to exchange up to 20 million packets per second and minimum packet size. So that's pretty impressive if you want to implement some sort of fast packet processing application in your machine. Or you can pass through a hardware port. In this case, this is a sort of direct assignment that you can, of course, implement using standard PCI pass-through techniques. But it may still be interesting because you can implement direct assignment without IOMMU supporting the hypervisor and without actual support for PCI pass-through. So it's just a different way to do the same thing. From the point of view of the guest operating system sees a virtual NIC. Okay, and the virtual NIC has the very same configuration as the underlying network port. So if you pass through a hardware NIC with 8 receive rings, you will see a virtual NIC with 8 receive rings within the virtual machine. And again, there is no overhead in terms of copying, because the guest has direct access to the buffers and the rings on of the real port. So you can do basically zero copy from within the virtual machine. Any sync commands are basically forwarded to the host. So this is an example of application that you may implement with this system. It's a very simple 2 ports application. So we have an external port. Think of it as a public port on some network, and an internal port. So you want to forward packets from the receive rings of the external port to the transmit rings of the internal ports, and the other way around. And when going from the external to internal, you also want to apply some rules. So I don't know, depending maybe on destination IP or destination port, you may want to drop some packets or select some packets. While on the other direction, you don't want to filter. Okay. How do you do that in in a few lines of code? So this is the main synchronization logic. First, we open 2 ports, okay, so the internal port and the external port, using a very simple library. And then we have a simple poll-based loop, for loop. Okay, so this is the poll. So here we have 2 ports, so we have 2 file descriptors, 1 file descriptor for each port. What we need to do in this simple forwarding application is to decide which events we want to wait for. So the logic is very simple. Let's take the external port, for instance. So if I have no packets ready to be received on the external port, what I want to do is to poll in to wait for them, okay, on that file descriptor. Otherwise, it means I do have packets. So what I want to do, since I want to forward on the other port, I just wait for egress space on the other port. That's why you poll out on the second port. And this is specularly for the other direction. So if I don't have any packets ready to be received on the internal port, I wait for them. Otherwise, I wait for egress space on opposite port. And then I call the poll function. When poll returns, it means that some events are ready. And so I can forward. And I forward in both directions, right? From the external to internal, and the other way around. This is the function that implements zero copy forwarding. It's interesting. What I'm doing here, is just a parallel scan of two rings. So what I want to do is I have a receive ring from the source port and a transmit ring of the destination port. I want just to forward a bunch of packets from the receive ring to the transmit ring. So I do a parallel scan, and the nice thing is that with Netmap you can implement zero copy forwarding. So each descriptor within the ring has inside a buffer index, and the buffer index is the identifier of a buffer within the net allocator. So all you need to do to forward from a ring to the other is just to swap the index of the two descriptors. And this is what I do here, and adjust the len, of course. I also need to tell Netmap that the buffer has changed, because it may need to change the DMA mapping inside the kernel. But otherwise, what I wanted to show here is that you can implement some simple forwarding rule in a very elegant way and simple way. So this is the example you can run. I have a QEMU virtual machines and two pipes. So I could have implemented a different example with hardware ports, but pipe is easy to do because it's all in software. So I have two Netmap pipes. I pass through one end of each pipe to the virtual machine. So the virtual machine, which is a QEMU virtual machine, will see two pass-through Netmap ports, while the other end of the pipe are used for packet generation. So here I generate a stream of packet, and on the other end of the pipe I receive. And so what I measured here with short packets, so 64 bytes, I measured about 17 to 20 million packets per second, which is pretty impressive, because consider that this application is implemented with just one thread, okay? While with full MTU size, so 1500 bytes, I get about 8. I actually tried to both zero copy and copy, and it's interesting to see that in the copy case, actually for very short packets, the overhead of changing the DMA mapping, because you need to do that, is actually higher than copy. So with short packets actually makes sense. And this is actually the same that Luke was saying before. So with short packets, actually doing things in CPU, copying, once you have something in cache, you can very easily process them. Okay. I also prepared a very short comparison between Netmap and DPDK. There is no time actually to go through this, but what I wanted to show here is some comparison item. So one advantage of Netmap and also XDP actually is that it's very easy to set up. Okay, so with DPDK, you need to care about huge pages, you need to care about IOMMU, you need to bind and unbind drivers from the kernel driver to the DPDK driver. While with XDP and Netmap, you just have to do nothing. Actually, with XDP, you need some very small eBPF program to redirect your packets to an AF XDP socket. Also, the other advantage that you get by reusing kernel drivers is that you can reuse the standard EPROUT2 and ATH tool tools, while in DPDK, of course, you need to rewrite ad hoc tools. Also, the threading model is a little bit more flexible, because with DPDK you have you have L cores, so you write your code, and your code is run in the context of a DPDK callback on a core. While with Netmap XDP, you can AF XDP, you can basically open AF XDP sockets or open Netmap ports wherever you wish, and run your packet processing code in any thread, right? Another advantage again of Netmap over DPDK is that you can, and this advantage is actually shared with XDP, is that you get standard synchronization tools, so poll, epoll, and select. Actually, with DPDK, you can use receive interrupts, but that's a bit harder than just using the standard system calls. Of course, DPDK has extreme performance. So when I prepared this comparison, it's very clear is that if you want the best performance, you must use DPDK, because with Netmap and AFXDP, we are still using system calls, so that has an overhead and comes with advantages in terms of improved isolation, standard synchronization. But if all you want is performance, you should use DPDK. Okay, conclusion. I showed you a very simple example of how to write simple but efficient Netmap application. I think the design principles behind Netmap are important. They inspired XDP because in the comparison it's very evident as many choices taken by Netmap and XDP are similar. Why do you want to use Netmap? It's the biggest advantage, I think. It's easy to set up, very simple API and standard synchronization. Of course, it's a smaller project than the other project, and it's easy to integrate with existing application. Okay, while for instance with the DPDK, you usually need to write your application from scratch and make your application fit within the DPDK framework. Of course, you can get higher performance. If you want to reproduce the tutorial, this simple setup, you can just follow the tutorial's link, and there are detailed instructions on how to reproduce that, all the code, and get those numbers. Thank you. I'm ready to accept questions. Questions?
Thank you so much.
Thank you.
So we have 5 minutes now before the next presentation starts. So just use the opportunity to remind people that could you please leave Vincenzo feedback through the FOSDEM website. There's a feedback at the end of the link at the end of the talk. And also I will plug the meetup this evening at the 9 Game Piss bar on the first floor at 7 o'clock. Yeah. If you're exiting, can you please exit from the back of the room?
Are you working with the author?